Students, I think, would benefit from choosing SWOCC because it gives them an opportunity to get involved at a more hands-on level earlier in their career. Students choosing to come to SWOCC benefit from having opportunities at the freshman and sophomore level to get involved in research that can carry them forward in their career while still maintaining the same academic rigor as they would experience at a four-year institution. The day in the classroom in physics and engineering starts out as sort of a conversational approach to the material that we're looking at, whether it be solving rocket science problems, whether it be designing bridges, whether it be designing electrical circuit systems. It's usually a conversational approach that leads to a lot of questions. I always tell students if they're doing science well, they'll always leave science class with more questions than they got answers to begin with. And that's to drive the intellectual curiosity of the students. And that's what I try to do, making things interactive as possible and letting them foster that curiosity and develop those critical thinking and teamwork skills that they need to succeed as they go forward. You're dealing with a class in physics that's typically between 10 and 20 students. That gives you plenty of time to interact, ask questions. You get more direct responses from the instructor. And SWOCC being a small enough school, there are instructors that you will see a number of times, so you get to develop sort of a rapport with your instructors and truly do become more like mentors than they do become teachers. The biggest thing it brings is a sense of opportunity. It gives us a chance to revisit how our curriculum works. It gives us a chance to incorporate new ideas, new equipment, and it also provides the students with ample opportunity for new projects and new developments in terms of research. The physics and engineering programs at Southwestern are a great way to begin your journey in a professional STEM career.
Good evening, everybody. Thank you for coming. I hope you've had the opportunity to take a look at our posters back there. We have Dr. Pertermann's students with sociology and anthropology has been working really hard on their posters. My name is Crystal Hopper, and I am our Oregon NASA Space Grant Consortium PRISMS project coordinator here at SWOCC. I work with our student researchers that you will be meeting here in just a minute. I also work with Dr. Coiner and help with a variety of things with the physics and engineering department. I'm so happy. This event each year is just so exciting because we get to really just highlight all of the hard work that these student researchers have been doing. SPEAR is the name of our student research team, and I'd like to have each one of them come up here so that they can take a moment and introduce themselves really quick before we have their presentations. They can kind of talk a little bit about themselves for just brief, if all of you guys want to come up here. Okay, here you go.
My name is Zach Warner. I'm an electrical engineering major here at SWOCC. I'm a non-traditional student. I'm old. GED graduate 2019. Went straight into SWOCC with a tuition waiver and have been here ever since. Background, why I want engineering, or
Just whatever you'd like to share.
Engineering is interesting to me. It's literally how the world works, how things work, how things interact with other things, innovations, ideas, inventions. So when I graduated my GED with a high enough score in sciences and mathematics to get a tuition waiver, I wanted to do something in a field I could see myself doing for the next 40 years. And when I did some fairly rigorous research, I found engineering field has very good job security, and it's exactly what I like doing. I was taking stuff apart when I was a child, trying to figure out how to put it back together. That's what I get to do now. I try to figure out how to put stuff together and make it work. So, yeah, I settled on engineering. Yeah.
My name is Aiden Lilienthal. I graduated from Myrtle Point, which is like 40 minutes down the road here, which is a pretty small school. I think that's probably the biggest benefit I have here from SWOCC is SWOCC's a smaller school rather than transferring straight to like Oregon State. I'm in the mechanical engineering program focusing in product design, and I'll be transferring to Oregon State in this fall.
Hi, I'm Damian Lilienthal. If you can't tell, we're twins. I also graduated from Myrtle Point. Like he said, the benefit of a small school, it really pushed us to go out and attempt pretty much every college credit that we had the opportunity to take. And I think that's what really pushed us into those higher level, math classes, engineering classes, anything that we had the ability to do hands-on anything, design work, any critical thinking, any of that. We both took the opportunity to take advantage of that. And I think that's what really started my want to be into engineering was that critical thinking. I've always been into math. I've always had some sort of creative mind, and the ability to be able to put all that together is what really drove me. I'm also into mechanical engineering. I'm hoping to eventually pick up at least a minor in some aerospace. That's kind of on the back burner to see, kind of where it goes here in the next couple of years, but that's kind of where I'm at.
So hello, my name is Ian Wakeling. I graduated from North Bend High School last year, freshman here this year. I'm in our physics program, and for me, I chose physics because I really like math, but sometimes I don't understand what our math is actually being applied to. And with physics, I can actually see what that math is going into, and I can actually see what I'm doing with it. And that's something I really love and enjoy. Being able to be here at SWOCC this last year, it's just been a really great opportunity to actually get to participate in these like actual student research projects and actually, get a taste of what it would be like to go out there and work at like with the bachelor's, with the master's at like a job. So, yep, here for another year.
All right. Hello, everyone. My name is Jake Bullard. I am a physics major as well here at SWOCC. I'd like to kind of pursue a theoretical or mathematical or particle type physics as a degree, and then also move into some astrophysics, and might as well throw on some math because math is still cool. And yeah, I just think it's super interesting, all these complex topics that kind of get into that you get into with like the theoretical physics and such. And I will actually be moving on after this spring to Oregon State University, where I can start pursuing some of those things.
Hi. Yeah. Oh, it's just. Hi, I'm CJ Morgan. I graduated high school in 2006, so I definitely fall under the non-traditional student category. I am working on my degree in physics right now. When I came back, I was wondering what I should do, get things in order, and slowly over time, I was just bullheaded and threw myself into the physics degree, even not knowing what to expect from myself, and got into SPEAR. And because of SPEAR, I've come across a lot of opportunities that I didn't think you could get at a community college level. Soon I'll be doing a presentation on a research paper. And because of this research paper, other graduate students I've talked to who've done research or other professors, listening to their stories, I've come across similar experiences in my process. And then as well as just the opportunities we'll be talking about, asteroid research, which really engages people. So the research that I'm doing, people will sometimes glaze their eyes and lose interest. But once we start talking about asteroids, then, engagement in science, and it's then becomes a fun topic instead of me meandering and talking for 20, 30 minutes But in the future, actually, this fall, I'll be going to OSU to pursue astronomy degree.
Sweet. Does that mean, I also have to go over here? Hello, everybody. I'm Caleb Ostemo. I'm another physics and computer engineering student here at SWOCC. I'd say I'm another not necessarily traditional student. I'm not quite as old as these old farts over here, but I wasn't very, academically inclined in high school. I didn't have too much care about school, but then after high school, I took a couple years off and kind of started getting really involved with just kind of physics and kind of just general academic stuff, I guess, on my own, and came to the realization I just kind of wanted to learn that type of stuff. So I came here to study physics and kind of got involved with the physics program in SPEAR here. And then I believe like halfway through or something like that, I kind of wanted to be working with like computers and stuff like that. So I got in with the computer engineering program as well. So yeah, that's kind of where I'm at, and then started doing even more research, and now I'm one of the leaders for the research groups for SPEAR. Yeah, that's about where I'm at.
Everybody. As you can see, we have a great group of students with us, and we're so, Dr. Coiner and I are so proud of them. I think half of them are graduating here in a couple or few days, it seems, and it's going to be tough to see them go, but I'm excited to have them be able to go on. With PRISMs, we've also had an opportunity to connect with our local educators through our K-12 STEM outreach. We actually have also been able to purchase a portable planetarium, which is going to be here soon, and that's going to be exciting for the community. We have an upcoming STEAM Academy for students 7th to 12th grade this summer. And so if you know of somebody that would be interested in that, please reach out to us and we'll kind of guide you through the process of getting them registered. But for now, I'm going to go on and we're going to start with, looks like Zach and his group, and to talk about our first project. And we'll have an opportunity to ask some questions at each one of these two. Thank you.
You guys can come up if you want. You can stay down there. It's up to you. All right. So I've been working on something I call the ERS, Energy Reclamation System. A little backstory there. Last year for the summer, I was part of a program called INCAS. A couple of our other students are currently a part of it. Yeah, you can dim the lights. But during INCAS, I actually was granted the opportunity to actually travel to Armstrong Research Flight Center. Sorry, I said that backwards. Armstrong Flight Research Center on Edwards Air Force Base in NASA. It was great. And the team I was with, we were tasked with this project to do a gap analysis on advanced air mobility, mainly electric aircraft, try and find a gap and see if we could find some way to bridge it. So with that backstory, what we ended up doing was we came to this idea that electric aircraft right now are extremely limited in their flight range. They can't stay in the air for very long because of the amount of power it takes to literally lift off and continually fly. So we came up with this concept where we would take, on this picture here, copper coils line the inside of a cow that would surround a propeller with magnetic tips. And as it spin, Faraday's law of induction would generate EMS or voltage that would allow us to take some of the kinetic energy being put into the propellers and reclaiming it as electrical energy and return it back to the power system, the power banks. So originally this was applied to conceptual make-believe huge cargo plane that we were, like we said, gap analysis. But the big highlight right here, if the charge generated from the ERS is significant enough to charge the cell in the charging state before the active cell needed to cycle back into a charging state. Sorry, thank you. Then the aircraft would theoretically be able to fly extremely vast distances if it even needed to land. So currently, this is the X-57 NASA's electric prototype airplane. I got to see this thing in person. It was really cool. But as you can tell with this guy sitting in the front, it's pretty small. This is a two-seater. It's behind him is 800 pounds of lithium-ion batteries. This thing has a flight range of 100 miles. If you think about that, this guy gets to take off, do a loop, and land, and then he's done. 100 miles is not very much, especially for a plane this small. So this premise, we decided to do a project where we're going to, like I said, the CAL, we're physically building a mini model based off of this engine right here, permanent magnet motor. It's got 3 props. We have both 2 and 3 props. You'll see here in a second, kind of because of how I built the CAL. It's now 2-phase, but I'll get into that in a second. But so the goal behind this experiment is we're actually building a mini mock-down model to actually see this is all a theory at this point. So we're actually trying to prove whether or not we'll be able to reclaim enough of the kinetic energy back as electrical energy in order to make this a viable trajectory to pursue. Here we had some fun designing our little mini model. Bobby, who's not currently here, did the initial stage development on SolidWorks. Aiden picked up the slack and got us these. We had a lot of fun print attempts that you can ask him about in questions if you want. But so there's our CAL printing. This is what our little mini model looked like once it was finished. I just threw some wood together, put a speed regulator on the back, and it's got a DC voltage or DC. I can't think of the word. It's got a motor on it, a DC motor. Nothing overly fancy. It's really not. You can see inside here, it's got these cutouts all around. Currently, they're empty. This is where we're at right now. Well, the last slide's where we're at right now. We don't have the coils wrapped. That's the next step. We're actually going to have to wrap 16 individual coils, 8 clockwise, 8 counterclockwise. We're going to have to feed them in here, run them, wire them, and then here's actually the circuit diagram, super high tech, fancy on a whiteboard. But this is literally everything all the way through rectification from AC to DC. So anybody that understands electrical circuitry, hopefully that helps. Anybody that doesn't, again, ask me questions at the end. But basically, these are the pickup coils. As the propeller spins around here, it'll generate 1 phase in the blue and 1 phase in the green that will go to these rectifiers that will trap, that works, but it'll convert AC into DC voltage current, where we'll have a capacitor, doesn't really matter what, to create a load, and then some unknown resistor, where we'll have just a single lead out, where we'll be able to measure everything and see if we're getting enough energy back. That's where we're at right now. I took that picture yesterday. So we actually have everything up to the point where we just actually have to put the coils in and measure it. Once we do that, we'll be able to, we're actually at a point now where we're going to be able to start calculating the magnetic field, flux, density, all that to actually start building a mathematical model. Am I missing anything? Magnets? Magnets, okay. Currently we have the magnets embedded into the tips of the propellers. This not necessarily the most ideal configuration, but we thought it actually was pretty sly. Because we actually have the way they're in there, there's a magnet on the front and a magnet on the back with a little sleeve in between. They're holding themselves in. There was we can take them in and out as needed, and we can spin this thing. It's only spinning, I don't know how fast it's spinning there, but this thing's capable of spinning at over 7,000 RPM. We don't need it to go above 3,000 for comparison with the actual X57 engine. So they don't fly out. Nobody's got hurt. So. Yeah. The team, I'm Zach Warner, the lead. These guys and Bobby are assisting research, whatever we are. Aiden, Bobby, Damien, and Jake. Braden's not here. I haven't really put him too much to work yet, but he's going to be doing the main bulk of the programming. And then consultants and mentor Dr. Aaron Coiner and the electrical engineering professor Fraser Pruitt, who's not currently here either. And that's kind of it for me. So anybody have any questions? I mean, you can ask me questions anytime, but go for it. Yeah. I'm not actually going to capture right off the bat. So right now I'm trying to measure how much charge. So the motor I have is I still can't think of the word, but I can go anywhere from 12 to 18 volts and anywhere from 1 to 3.2 amps to turn the motor itself. So if I can capture, if I rectify and regulate the voltage back down to 12 volts, and I can get at least 1 to 2 amps to come back with it, then it's viable. Because then I can actually I don't even need that much. If I could get half an amp to come back, it would be viable. But if I could get enough to actually power the system, like unplug it while it was running and it stays running type thing, that, I would jump for joy and this thing would be like the greatest thing ever. But any other questions? Do you have your hand up? Yeah?
But I can come up.
No, behind you.
Hold on just a second. Oh, here.
Oh,
I'll run for you.
sorry. Thank you.
Yeah. Just talking.
What's the coolest thing you've found with your research so far?
That is a great question. We've had as far as to our research in particular, I don't know if we've made any groundbreaking discoveries yet that I can claim as my own or anything. But I mean,
Self-teaching yourself.
yeah. Just the entire process is honestly, yeah. I don't know how to answer this right. This is a really good question.
I think that's up for you to decide.
Yeah.
This, right?
But spinning magnets. Yeah, I don't know with the single greatest thing. That's really tough. I love seeing this. So some of these aspects are like the whole thing what I just said at the beginning about Faraday's law. I didn't know what that was 2 years ago. And I didn't have a clue what that was 2 years ago. So now not only do I have what I like to think is a firm understanding of it, but I get to play with it. I get to spin magnets around and see how much electricity I can make. Can I make enough electricity without hurting myself, or am I going to hurt myself? Never know. But I don't know. I like playing with electricity. So is there any other questions? All right. That's it. I'm on.
figure this out up here. Hopefully. Hello, everybody. Does that work? Right here? Oh, there we go. Okay, so I believe I will be. Oh, there we go. Hello, everybody. I'm Caleb Ostemo again. I am the leader of SWOCC's the SPEAR team's micrometeorites collection and research group. So it's pretty much exactly what it sounds like. We look for, or we collect and try to look for micrometeorites. Oh, that's right. There we go. So these are micrometeorites, just so I can give you guys a little bit of background so you can look at it. These are barred olivine, which I can kind of get into what the different, like how you find different types in a minute. These are the barred olivine. These are like cryptocrystalline, I believe is the type that they're called. And then this is just, it's called glass. It's just because they're mostly comprised of glass. And there's something called scoriaceous micrometeorites. And those are all just different kind of types of micrometeorites. And what a micrometeorite actually is, it's there's little like very tiny particles that float around in space. And it's actually often referred to as space dust. And once they actually, in those, it's, you know, they fall through the atmosphere and they're like little meteors. And once they hit Earth's, the surface of Earth, they're actually little meteorites. So that's why they're just microscopic meteorites. And how they're actually like, how we define the different types is just basically the way that they fall through the atmosphere. It's because they often they reach different temperatures and they have somewhat different compositions, kind of just based off of like what they're made of. And that's really how we identify the different types, because the different temperatures will kind of determine like how much of glass or how much glass they're made out of and how they cool can kind of help determine like how much crystal is developed inside of them. And this is, it's pretty interesting. It also makes it a lot harder because these are comprised, a lot of them are comprised of something called chondrite, which is just, it's another thing it's referred to as just space stuff. It's just kind of different elements and different like chemicals that are found around the entire universe comprised in one thing. It's just kind of a common name for space stuff. And it's also very interesting to research. I keep forgetting this button doesn't work. It's also very interesting to research because it's found that they really only fall for about one micrometeorite falls for about 1 square meter per year. So that's kind of why we want to research it, is to kind of give updates on that. And then also, kind of update that. And it's also can update kind of it's kind of a new thing to actually look for micrometeorites in more urban areas, because it used to be really in just kind of desolate areas and very empty areas is where we used to look for micrometeorites, just because not as much is really going on there, and it's much easier to find, you know, like those little particles, and it wasn't really believed that you could be able to find micrometeorites in a more urban area just because of how much industrial waste and stuff like that is found around here. But it's being found that it's actually just, you can go out and, you know, collect micrometeorites. So that's really our mission, is to kind of update data on micrometeorites and finding them in urban areas, you know, what the different kinds are and how frequently they fall. Which kind of every time. Which brings us into our process. That's Zach up here, our guy who just presented. He's actually laying one of our traps right there. And here's just kind of an example of what we're looking at. This right here is a needle under a microscope, and this is kind of like an ideal candidate that we look for. It's kind of a little bit of a size comparison. So to get into our actual collection process, these right here are what we call magnet traps. It's exactly what they sound like. They're magnets that we use to trap, you know, metallic surfaces or metallic material. So what we do is we just put these magnets in these little bags and stuff them. You can see he's stuffing it into like a weather drain right there. So what happens is when it rains, it'll kind of just disturb the sediment on roofs, and that rain wash will go down the weather systems, and then as they come out through these the magnet traps will kind of collect any type of metallic material that is falling through there. And that's really just how we do our collection process. It's pretty simple, metal things are magnetic, so we set magnets in places where we think we'll catch them. Which then after we do collection, we do a little cleaning process, which is it's very necessary because one, there's not everything you get is going to be a micrometeorite, and not everything you get is even going to be like a rocky material. So we'll do kind of an initial wash through one of these beakers right here, which is just filled with soapy water. So we'll throw the collected sample into that beaker and just kind of disturb it. And that'll wash away, like any mud or organic material. And actually the organic material will float to the top. So you can kind of just decanter that out of there, which makes it a lot easier. And that's what this entire cleaning and then the entire cleaning process is just about, kind of minimizing your sample process, just because there's not so much to go through. So once you do your cleaning, you run it through one of these coffee filters, and that'll just kind of get some extra cleaning in it, basically. And then once that dries, you run it through this series of sieves. And that's another step in kind of minimizing your collection. And it's very useful also because it's commonly found that micrometeorites are only in a range of 400 and 250 microns, which is fairly small. So, having this huge, I think it's 4,000 to 63 micron mesh sizes eliminates quite a bit of sample that we don't actually need or want to have to process through. And once you run it through those sieves, it is time for the analysis process, which is, once you run it through the sieves, these are all of our collections that we have currently. We just put them into petri dishes and look at them under the microscope. This right here is a picture under the microscope, which is just one of our samples that we're looking at. And that is a fairly large sample. If you can imagine, looking at a microscope, I think it's about 45 times magnification. So, it's just a tiny little speck out of that entire petri dish. So, looking through that to try and find something like this is quite difficult. That's one reason why we want to go through the whole washing and minimizing process. But yeah, that's pretty much, what we do. So so it's passed through the sieves, and we pass it to these petri dishes and then and then analyze that sample under the microscope. And we're just trying to look for those small little, we're trying to identify, micrometeorite candidates is what we're doing. And those will go through kind of a different, about two processes. So we try to find it in one of these samples, and then we transfer it to, it's kind of hard to see, but one of these tiny little ones. And then we try to look at it even further just by itself so that it's a bit easier to try and identify. But once that's done, that's pretty much the entire analysis process. And once we have the candidate, we just this is our little corner of micrometeorite candidates right here. And once we have collected enough of those, we'll actually transfer them to a facility, I believe, either OSU or PSU. And they both have electron scanning microscopes, or scanning electron microscope, there we go, which can identify the actual chemical makeup of the different micrometeorites that we've identified. And they'll be able to confirm if it is like an extraterrestrial or an Earth-made material, basically. And so that's pretty much our entire process of, collection, cleaning, and analysis. And this is actually kind of better picture of what we're looking for. These are two kind of ideal, I believe Discoraceous, if you guys remember back a few slides, micrometeorites. And these is actually a good example of things that are often mistakenly identified as micrometeorite that we found. And these look a lot like examples of just of industrial waste, basically, or industrial byproducts. It's actually a good time to bring up basically how we identify like what a micrometeorite candidate is we use this book right here. It's On the Trail of Stardust, which is going back. It's commonly not thought that you could really find micrometeorites in urban areas, but the author of this, I think John Larson, he kind of got interested and started collecting stuff in urban areas and found that it actually you actually can. So he basically just wrote a guide about, like the history of micrometeorites and how he started his process. And then he also included a lot of pictures of micrometeorites that he has found. And that's basically how we identify our candidates, is we compare them to the pictures in his book, which I think, yeah. So this is from that book. We try and compare just basically textures to the pictures in the book. And that's how we identify our candidates. And this right here is another sample, is about average size sample. So this is a bit better, but you can see, we'll try to look for something kind of like, if you see that little guy right there, we'll look for that, or like these up here or that. It's, just going through the whole process, trying to find something that looks about right. And then, just doing further analysis. And this is another just size comparison, so you guys can see a bit better what we're looking at. So this is the same picture as before, just the micrometeorite next to the needle under the microscope. And this is, I believe, the same candidate that I found. And this is actually just on the tip of the needle, and I took it with my phone, so it's a bit better perspective, not under the microscope. So this is about how small the samples that we're looking, or the candidates that we're looking at. So it's a bit of a tedious process. But however, so far we have collected about 30 samples, and that's throughout. A lot of them have been collected here at SWOCC, on the SWOCC campus, but we have also done stuff. We've also collected from the Bay Area Athletics Club and from the previous Starfall leader's home. She did some collections out there, and that's been, and out of those 30, we found about 27 micrometeorite candidates so far. And here's some just pictures, so that, and some more just examples. These are the two from the previous slide right there. These are pretty good candidates for this Scoriaceous micrometeorites. Sorry. And then this is another one up here. This is, I believe, barred olivine or olivine, something like that. But that's the most common type of micrometeorite that is found, just kind of on average. And then this is another good just example of those candidates we thought are probably more likely industrial byproducts rather than micrometeorites. And there's a picture that it's another really helpful thing from this book, is he provides lots of examples of things that might trick you into believing they're micrometeorites, but they're actually not, which is a lot just like these industrial byproduct things, which is, often found by like welding shops or construction sites, stuff like that. And so what we want to do next is really, need to expand our collection area, which is just, our collection sites, or the number of our collection sites. And that's because, like I said before, statistically, it's only really 1 micrometeorite falls per 1 square meter every year. So that's not, we have a limited sample size that we can actually collect, and we want to be getting as much of that as we can. So we need to expand our area, and that will really only, doing that will only accumulate into more candidates that we actually find and can identify. However, to do that, we really need to expand our research group, because going through one of those samples can be anywhere from like 15 to 30 minutes just for one of the samples. And it's quite a bit of work, for the, setting up the traps, doing the collection, doing the cleaning, and doing your analysis. So it's really, before we can start really expanding our collection area, we need to expand the actual number of people in our research group. So that is about where we are at. I believe that is, yeah. And these are my references. Are there any questions? Yes.
So you guys put out magnets to collect all of them. What about non-magnetic?
That it's a bit more annoying because it's really, you just have to, like, you have to go like shovel stuff and then process that basically. And, just don't necessarily have to do that. I mean, on the roof, I guess there are ways to do it where you just sweep up the sediment on roofs and then try and go through that, but it's a lot more to process. Because you're also you're going to be getting, the magnetic material and the non-magnetic. Yeah. Yeah.
So so you started out on this project last year, working with Ellie.
Uh-huh.
So what are some of the biggest things that you've picked up on this project as you've sort of transitioned to being the lead?
Biggest, I guess complicated of a simple process it all is one big thing. I mean, looking at it, it's just kind of think of it as tiny rocks, but it goes into a lot more depth, I guess. And it's a lot more fascinating than, initially thinking, because you get into stuff like thermodynamics and stuff like that. When you're like, I don't know, when I did my presentation for physics, you go into the actual, physics on how they're made as they fall through the atmosphere and stuff like that. That was really cool. And then another thing I found is how different you perceive things under a microscope, like the movements of your hands, or how small a tiny little sample is. That was also pretty cool. All right. I should probably turn it off. You clip it to your thing and then turn it on. That's how I figured it.
Computer science major.
Okay. Am I going to get this to work? We shall see. Whoa. Does that sound okay or not? Good? Good. Okay. Put this on.
It's on the top, there's a little switch. Turn it on. Oh, you're leaving the clip it? I just put it in my back pocket. No problem.
Okay. Difficulties. Okay. All right. Good. All right. So, hello everyone. My name is Jake Bullard. I have already introduced myself previously, so we're just going to jump straight into this. I will be as briefly as I can talking to you about baryon asymmetry, which to me is really an incredible story of chance. Before we get into that, I will just kind of outline what we're going to go over tonight. So I'll provide you guys with some background on what baryon asymmetry is and just kind of like some necessary context for the idea. Then we'll go over where CP asymmetry has been observed, both past and present. CP asymmetry, we'll get into what that means in a little while. And then we'll take a somewhat more detailed look into CP asymmetry itself. And then finally, we'll conclude with some implications of that research. So that's probably a good place to start out at the assumptions that are made here. So in all of the research, the big assumption that is made is that the prime event, or maybe more commonly known as the Big Bang, is an accurate description of the universe, or it's assumed to be a true description of reality. And for those that may not be super familiar with this idea, it's the idea that approximately 13.7 billion years ago, all matter, time, and energy was contained in a very extremely small, dense point. And there was some instance that a trigger caused this point to rapidly expand, releasing or creating all the matter, time, and energy that we see today. And I want to touch more on this last point here in just a moment. but it's also proposed that equal amounts of matter were created at the Big Bang. But before we get into that, the other assumption that maybe the audience might have tonight is that I know what I'm talking about, and I'll be the first one to tell you I have no clue what I'm talking about, which maybe is not entirely true. I have like a slight degree of I know what I'm talking about, but 99% I don't know what I'm talking about. So yeah, this will be fun. So, statement of the issue. Going back to what I just kind of previously said, all matter in the universe was created by the Big Bang or the prime event. And I really want to touch on what it means for all matter to be created, because it's not just the matter that we see around us. It's also the dark matter, and also it created all of the antimatter at the Big Bang or the prime event. So then where is all of this excess dark matter? All I see and feel and touch and hear is, I don't know if you can hear matter, but whatever, is ordinary matter. So where's this excess dark matter? And that's really the question, the core question of this problem, baryon asymmetry. Because it seems nature seems to have some slight preference towards ordinary matter. And I mean slight in a very big way, I guess, because it's approximately one surviving particle of ordinary matter to the approximate 10 billion annihilations that would have occurred. So getting into some of the background, before we kind of talk about antimatter, it might be a nice kind of introduction just talking about ordinary matter in a little more detail. So for maybe some of us, we might think that the smallest unit of matter is the subatomic particle, or the things that make up an atom. And I'm here to tell you that that's not quite the case. There are quarks and leptons, which are collectively known as fermions, that actually kind of are smaller. And there's a little asterisk there because the electron, which is a subatomic particle, isn't actually made up by anything else. It is a fundamental particle of matter in the lepton family, but quarks, however, are smaller than the subatomic particles like the proton and the neutron. So in saying that, the quarks are actually what constitute those different particles, and those quarks and leptons are currently what we understand to be the most fundamental unit of matter. And along with a couple of other particles, the fermions and those other ones actually make up the universe around us and kind of describe it. And to more readily organize what all of those particles are is the Standard Model, which is pictured on the left here. There are 4 different categories here. So you have the fermions, or the quarks and leptons, which is the outermost circle. And on the inner circle, kind of in the orange, is the bosons, or the force carrier particles. And then right there in the middle is the Higgs boson doing its own weird little thing. And so I want to take a little bit of a closer look into quarks, because they're going to be kind of important for this discussion. And so, as I previously mentioned, they are one of the most fundamental particles of matter. And as of right now, there are currently 6 different types of quarks that each come in kind of like 2 pairs, or they're more formally known as generations, where you have generation 1 with an up and down quark, generation 2, charm and strange, and generation 3, top and bottom quarks. And if I go back, so generation 1 is going to be the up and the down, charm, strange is generation 2, top, bottom is generation 3. And these generations are kind of describe like the mass, I guess. So generation 1 is going to be your lightest particles, generation 2 kind of medium, and 3 is going to be your like heaviest types of particles, which is important because as you increase the mass of each particle, so as you go up in generation, those higher generations are going to be less stable. So they're going to want to decay into more stable generations, and most likely will result back into generation 1. So now I'd like to talk about actual antimatter and its interactions with matter. So antimatter really is just an exact copy of matter, except for the associated charge. And again, there's another asterisk there because, well, someone might say, like, what about the neutron or the neutrino, which has a overall electrically neutral charge? There are then other types of charge that are opposite in antimatter, like lepton number. So that accounts for what the antimatter particle is. So just like ordinary matter, there are also antiquarks and antileptons, and all of these types of particles interact and behave similarly to ordinary matter. So how does matter and ordinary matter actually interact? There are really 2 overall ways that matter can interact, and this is kind of this idea of particle formation and annihilation. So starting with particle formation is when a particle, so matter particle and a antimatter particle come together. So like a quark and an anti-quark, which is what's going on in the picture. This is a picture of a meson, which is what particles are for matter and antimatter. So you have the up quark here and the anti-down quark here, denoted by the bar above the D. And so with these mesons, these actually can participate in what's known as mixing, and we'll kind of talk about that a little bit later. But for now, you can think of it as the idea of the spontaneous transformation from a particle or a meson to its antiparticle or antimeson, or vice versa. And this is typically done with the emission or absorption of a W boson. These mesons can also participate in decay, where, as we kind of talked about this already, it's the idea that it turns a particle of matter that's maybe less stable into a more stable particle. And then the other way that matter and antimatter can interact is this idea of annihilation. And it really is just kind of self-explanatory. Annihilation for matter and antimatter is like the definition of annihilation. Complete destruction ensues, as all of the matter and antimatter, all of their mass is actually going to annihilate or turn into or transform into the pure energy, which is pretty crazy. And so kind of at the core of this thing, or like a big idea around this whole topic, is this idea of CP symmetry. So kind of pushing us off here, we'll talk about what an actual, like what symmetry is in general. So by definition in physics, it is a law or operation in which a physical property or process has an equivalence in two or more directions. Okay, maybe some gobbledygook. I like to think of it as just like a transformation of some form that does not fundamentally break the laws of physics, which is typically a good thing. So there's also a similar symmetry for particles, which is known as charge polarity or CP symmetry. And so CP is a combination of two other symmetries, which is charge conjugation, or C, and polarity, denoted by P. And so P is the idea of like transforming something into its mirror image. So for instance, if I was walking so in other words, if I walk this way with, we'll say, positive velocity, applying P to me would then result in negative velocity of myself. And C is the idea that it transforms the charge of a particle or transforms a particle into its antiparticle and vice versa. So an electron would, when you apply C to it, would become a positron with it, which is an electron with a positive charge. And this is really integral to our discussion of baryon asymmetry, because so far, the violation of CP symmetry is the only observed kind of measurement of baryon asymmetry. So let's talk about where CP asymmetry was actually first discovered and where it's at now. So in 1964, in an experiment by Jim Cronin and Val Fitch, they had kind of a surprising, almost accidental result of finding CP asymmetry. And it has to do with these kaon systems. So you have a kaon, which is a meson that decays into two pions, and this is, they call it the short kaon, I guess, and this is the long kaon, which decays into three pions. And the whole thing with their experiment is that they sent these two different types of kaons down a beam, and they were only expecting to see the kaon long particles, because they decay in their decay is longer than the short particles, hence the name long and short. But what they actually ended up finding was that there was actually some 2 pion decays instead of just simply 3 pion decays, indicating that there was some sort of CP violation going on, which is now known as a mixing. Now, presently, CP violation has been observed in other areas, and one of the most notable being the B meson. And maybe some of the reasons for why it's more recognized is because heavier particles lead to easier theoretical calculations. So the B meson has like the bottom quark contained in it, which is, if we go back to a few slides to the standard model, that's one of the heavier quarks. It's also thought that for this specific system that results in like a 20% higher decay or probability for a decay, in that system, specific system, CP violation is thought to be enhanced. And this system is about the decay of a B meson, or charmless B meson decay, which just means that the bottom quark in that meson is not going to decay into a charm quark, which it typically does, which is why I guess the extra 20% there when it does not decay into the charm quark. And so now we'll kind of take a somewhat more rigorous look into what CP violation is. So broadly, CP violation is just an indication of some sort of difference between matter and antimatter. And it's somewhat the idea that, so if you apply CP symmetry to an electron with positive velocity, you should get a positron with negative velocity. And so CP violation is kind of the idea that you don't get that situation going on. And so CP violation can either be direct or indirect. And basically direct CP violation describes the effects appearing in the amplitude of particles themselves. Don't know what that means. I kind of don't know what that means either. It's fine. What you can really take out of this is that it relates really to the decay of a particle. So direct correlates to the decay of a particle. Indirect, on the other hand, describes the effects of meson-antimeson oscillations of a certain system. So in other words, transforming a meson into an antimeson or vice versa and oscillating between those. And another way of just think about it is it relates to particle mixing. But what's really interesting is that what scientists have found is that the observed CP violation isn't actually enough of an explanation to account for why there's still so much more matter in the universe. And in fact, it falls several orders of magnitude short of what we should be seeing. And so, to kind of figure out why this might be, there are some other ideas that have popped up, and one of the things is leptogenesis. And this is the general idea that leptons also contribute to the asymmetry problem, because what we've been talking about right now are the quarks, well, not the leptons, but this is the idea that leptons could actually contribute to the baryon asymmetry problem. And so the physicists Fukugita and Yanagida, probably butchered that extraordinarily well, proposed new particles known as singlet neutrinos. And the nice thing about this is that it actually provides a necessary new source of CP violation. And these next 2 points that they obey dynamically generated baryogenesis and deviate from thermal equilibrium, basically just kind of hints at the idea that there was not some sort of initial condition in the universe that would have made matter win out over antimatter. And to actually describe how these singlet neutrinos violates CP is that they violate the lepton number. The other idea that's been brought up is this idea of supersymmetry, or SWOCC. The main idea of SWOCC is that it predicts a particle partner for each of the particles in the standard model. So it basically doubles the number of particles that we currently know. And the SWOCC particles actually are supposed to behave very similarly to their standard model counterparts, but their mass and spin are just going to be a little different, where I believe the mass of the supersymmetry or supersymmetric particles are heavier, and I'll get into the spin in just a moment, actually. And what's nice about the supersymmetry model is that it would help fix the mass issue with the Higgs boson, because right now scientists are a little confused as to why the Higgs boson is so light. And so these supersymmetric particles would kind of help to cancel some of the mass and explain why the Higgs boson is so light. Another interesting property of SWOCC is that it relates fermions and bosons, otherwise known as the matter particles and the force carrier particles. So SWOCC particles differ by a half unit of spin. And so I guess I just mentioned this, the fermions, or the matter particles, have half integer spins, or like fractional spins, whereas the bosons have whole integer spins. So if you offset it by a fraction, or a half unit of spin, then you get fermions paired with bosons and bosons paired with fermions. And there's also some other interesting benefits as supersymmetry as well, and that it offers a way to unite the weak, strong, and electromagnetic force. It offers an escape from too rapid a proton decay, and it implies a solution to the dark matter issue. And then I'd just like to conclude with some thoughts. The asymmetry between matter and antimatter seems to be a fairly ill-understood phenomenon with very little experimental evidence to support many of the theories. The discovery of CP asymmetry with the experiment by Cronin and Fitch, although perhaps accidental, provided vital insight into the nature of matter and antimatter. Other theories were also developed that may have originated in part from this discovery as well, that focused on the shortcomings of the standard model. Some of the most promising, leptogenesis and SWOCC, offer convenient explanations that fix the errors of the standard model. However, experimental evidence to support these ideas have been all but non-existent. Whether this be a result of technological limitations or simply false descriptions of reality is yet to be determined. But what is the reality of what this all means? I would say that life is too fragile to waste it and not appreciate the time that you have. So I would encourage you to stop and perhaps take a moment to smell the roses, because it is, after all, 1 in a billion chance that those roses even exist. Those are my sources. Do you have any questions? Take a sip of water.
Jake, let's see real quick for the audience. You might want to mention the program that led you to do this research.
Yeah, that might not be a good idea. So I was actually able to kind of start this research a little while ago, like last year, with the STAR program through OSGC. And so basically that is the idea where I get to pick a topic that interests me. So in this case, baryonic symmetry or matter and antimatter. And I get to do like a research review of all the research that's currently out there, and then write like a white paper or a 6 to 8 page paper on what I found and kind of just some of the implications of the research perhaps. And then it's kind of the whole idea of the STAR program, which is pretty fun.
Questions or anti-questions?
Just set up.
It's here for my moral support. Wait, Jake, how's this go on?
So that's part you put on. So here, I can help you.
Physics students doesn't take. Here we go. Is it just on?
I think so.
Okay, can everybody hear me? All right, cool. All right, awesome. Does this thing work?
No.
Nope. Cool. All right. There we go. All right. So my name is Ian Wakeling. I'm here today with the Isaac Project. I've been a member of it for this school year, and next year I am going to be the team leader on it. So it's pretty exciting. I think it's fun. So what is Isaac? Isaac is the International Astronomical Search Collaboration. It's a monthly campaign, although we have a lot of campaigns in a year, for citizen scientists to search for near-Earth asteroids. So those are kind of asteroids that exist within the solar system. There are a lot of participants from all over the world that are part of this program. And currently there are over 400 teams that are active. And these teams, they come from places like Brazil, places like Africa, places like India. You can pick almost any country in the world, and you can probably find a team there that's helping work on asteroids, find asteroids, which is, it's pretty cool. It's not often that you get to see these international projects going on. So our team here is the Coastal Oregon Asteroid Search Team, and we are designated to be COR for Coastal Oregon Research. So these are the telescopes that we get our images from. They're called the Pan-STAR telescopes, and these are the Panoramic Survey Telescope and Rapid Response Systems. So we just call it Pan-STAR. It's a lot easier. These are 2 telescopes in Hawaii that are continuously looking at the sky, scanning it, looking for these near-Earth asteroids. Here on the right is PS1, and on the left is PS2. PS2 is the newer of the 2 telescopes, but both are great. They're both phenomenal. We mainly work with images from PS2, although recently we have been getting a lot more PS1 images, so that's been fun. So what do we do? How do we actually identify these asteroids? So we get these images from the Pan-STAR telescopes, and we load them into a program called Astrometrica. So Astrometrica, it's really cool, looks straight out of Windows 95. But essentially, we use it to do a thing called blinking images. That would be, we essentially play a series of images in a row over and over and over again, going through them. And it kind of makes like a like a short little video with a few frames. So to start off, we load up all our image set, which is comprised of 4 different images, into Astrometrica, and it's able to look in its database. Here you can see that in each of these images, it's found like 112 stars, 108 stars in its database, and it marks those out here in these green spots as reference points. Then it uses these reference points to help layer these images on top of each other. So that way when it starts blinking, it is, it's not going in different places and it looks like a video. So here, this is an image of a blink of an image set. And this is what we see. This is our main panel. So up here, if you notice, there is this little red dot that's moving. This is an object that was already found by the program, an object that's already in its database, that it's marked out for us. So it tells us that, hey, there's something here, don't forget it. And then here, this is an inverted version of the image. We like to use this because it's a lot easier to pick out stuff from the white noise. And we always like to say that it's easier to see, black ink on white paper than white ink on black paper. So let's say here, this is a big exaggeration of what we might actually find, but it's useful to talk about to kind of help explain this. So this right here, this guy here that's moving, this would be an unidentified object. So we'd see that and go, oh, that's pretty cool. So we start off we click on it and it brings up this screen. You might say, oh, numbers scary, but don't worry, it's not that bad. So we look for 3 things on here. The first thing that we do is we look at this graph. So this graph is the signal to noise ratio graph, and it just essentially tells us how likely is it that this is actually an object and it's not just white noise. So we're just looking for these dots to kind of fit the graph, and we can see that they kind of do. So that's the first thing done. That's good. The second thing that we look for is then this number here. This is the SNR number, and that's the actual signal to noise ratio, the data value. So in this case, that is a value of 10.6, and we're just looking for it to be over 4. So it meets that. And then the third thing that we look for is this R number right here, R equals 19.4, and that is essentially the magnitude of the intensity of the light of the object. And there, we're not looking for a specific value, but rather we're looking across all 4 of our images and making sure that that number is relatively consistent throughout. We don't want to see it be 19 and then 16 and then 23 and hopping all over the place. We want to stay around that 19 range. So let's say we find something and it meets all 3 of those tests, and we say, okay, this is probably an asteroid. So we're going to click on this little button right here, and it's going to pull up another screen with a lot more scary numbers. But don't worry, it's not as bad as it looks. So up here we'll see these 2 values stand for the right ascension, which is essentially how far up and down in the sky an object is, and the declination, which is how far left and right the object is. So you can think about that like on an XY plane. So here we can see that this is an object that's already in the system, and we can see that its coordinates are exactly the same as the object that we selected. So we know that, okay, this is most likely that object. So what we're going to do is we're going to highlight it, we're going to click OK, and it's going to designate that object for us. Here we found object 2001 FV103, or I2254, and we're going to look at it. We're going to say, okay, this is probably real. This is probably the object, and we're going to click accept. And so we're going to do that for each of the 4 images in the set, and we get this cool little blue circle around our guy, and that tells us that, hey, we found this object, and now we're able to continue on to other parts of the image and look for more objects. And then here's just an inverted version of the image to help kind of show that more clearly. So Astrometrica has its nuances. It very much so loves to cooperate with us. There are times when it just doesn't want to load images. Sometimes it doesn't want to blink the images. Sometimes it doesn't want to reference stuff. And sometimes it just wants to crash. And when we were getting images for this is when it decided to crash. So we put it in here.
This was a screenshot of frustration.
Yeah. So here's a more of an ideal example of something that we may actually find when we're going through these image sets. So next frame. So here we go. So we click on this little tiny speck right here, and that pulls up this so we can see in a bit more detail. And we're going to say, all right, is this an object? So we look here at the signal to noise ratio graph, and we see, all right, it's fitting the line. We look here at the signal to noise ratio number, it's a value of 9.1. All right, so that value is above 4, so that's pretty good. And we look here at the light intensity, and that is also consistent throughout all 4 of the images. So we know that, okay, this is most likely an object. So in this case, okay, we don't have it up here. So we do our due diligence. We check in here in object designation, see if this object already exists in the system. And we found that it does not. There aren't any objects nearby it. So that means that we found a new object. So what we would then do is we then label it. In this case, we label it COR, we're the Coastal Oregon Research, and we label it 0001, which is, that just means that that's the first object that we've come across. Right now, we are on our current campaign, we're at over 130 objects in total, which is really funny, and we are really hoping that we don't have the problem of going over 9,999 objects. So yeah, and then that will label the object for us right there. Moving on here, this is a much more likely case. This is something that we have to deal with, and this is a reason why they actually have humans working on these instead of machines, because machines can find those previous 2 examples. They are pretty easy to see. But this one, if you look up there on the screen, you can't see it. Even when I was looking at this on the small screen, you can't see that object there. But when you zoom it up and you have this red circle here, you can see there's like 4 pixels of it. So we see that and we say, okay, this is probably an object. So let's do our due diligence and let's check everything. So we start off by checking the signal noise ratio graph, and uh-oh, that's not good. That doesn't fit the graph. But we're looking at this. We're humans. We don't just see something and immediately throw it out. We can look at other stuff. So then next we'll check the signal noise ratio, and that's 2.8. That's below 4. So that's also an uh-oh moment. And so we say, okay, well, let's check a couple of other things and see if this is real. So then next we look at the intensity of the light, and we say that, okay, well, it's consistent across all of the images. So at least that's a start. And we also look at it as it's blinking through the images, and we see that it's traveling in a straight line. So we say that, okay, this most likely is an object. It's just not being picked up very well by the telescope.
Literally, I will pull a ruler out and hold it up to the screen to make sure it is actually moving in a straight line.
So we click on it, we get this screen again, and we can see that, all right, well, the declination is only 0.1 off. So that's pretty good. That's within 0.2, which is the tolerance for this. But we see here that the right ascension is 5.4, and that's pretty far off. So we know that, all right, this is not an object in the database. So that means we get to name it COR 0002, and you can see it circled there, maybe a little bit easier to see, and that's our next identified object. So that's a much more common case. But it's, that's why they have humans, and that's why that's essentially what we do. So once we go through an image set, we pick out all of the objects that we can find. We generate what's called an MPC report. An MPC stands for the Minor Planet Center, which is the main organization that's in charge of categorizing and cataloging the skies and all of these minor objects. So those would include things as big as dwarf planets, all the way down to these small asteroids and comets that are only viewable through these big telescopes. And then here you can see that there are all these lines of data. What these essentially are doing is they're just telling you about the objects. As you can see here on the left, you have the names of the objects. Here we have 3 sets of names. That means that we found 3 objects in this image set. And the top and the bottom ones each have 4 because we found them on all 4 of the image sets. But this middle one only has 3, and that might be because on one of the images, the object was out of view, or it went behind or in front of another object, and we just couldn't see it. But 3 is still good enough to confirm that it exists. It's moving in a straight line, that it's an object. So then once we get that MPC report done, we have a collaborative Google spreadsheet here, very fancy, that we work on as a team. For every single one of our image sets, we always like to have at least 2 people work on them, identify the objects. That way if one person misses an object, the other person can find it and spot it. Then we take those 2 reports, we say if we found any new objects and which object number they are, and then we smush those reports together and we send those off to Isaac. And Isaac is the people that go and take that and they send it off to the Minor Planet Center. And they're the ones who look at it and say that, oh, that's probably an object. We'll label that as a preliminary detection and we'll look into that. And this is really great because we're able to do this in a spreadsheet and everybody's able to do this on their own computer at home. That means that we can collaborate over big distances and we could have people literally anywhere in the world on our team helping to do this, even though we're located here. So that's pretty cool. Here is an example of one of our campaigns this last September to October. Each campaign is about 3 weeks in size. We get about 20 image sets. But here we had 6 objects that were classified as preliminary detections for our team. These are the 6 objects up here. And a preliminary detection for our team means that we were the first team to actually find these objects. There's always like a sort of race to see who can find these objects first, because remember, if you find it, you get to name it. So these 6 objects here were all attributed to us. And so now the MPC is going to go do some more research on these and make sure that they actually are real and that they exist. And as of last May, our team in total has a total of 37 preliminary detections, which is, that's pretty good. And that's 37 objects that we found. Out of 400 teams. So participation. This research is a really low barrier of entry because you can go home right now, go and download Astrometrica and start working on image sets. It is that easy. All that you would need to do is you need to register your copy of Astrometrica and you need access to a PC. And we say access to a PC because Astrometrica, it has its nuances. It doesn't like Macs. So yeah, we use PC. And also, Isaac really highly encourages student scientists. If you ever go to their page, there is always something there where they're promoting a middle school team or a high school team or a college team, showing off what they're doing. And it's really a great first step into the world of science. And this team has had the pleasure of working with the high school student in Brookings, Oregon. His name is Noah, and even though he's in Brookings, he was still able to be an active member of this team and contributing every campaign. So big thanks to these people here for their contributions over the course of the Isaac program throughout its life and helping to put together this slideshow. And here are some references for some of the stuff we got for this. So thank you. And then, we don't have a slide for it, but any questions?
I'll correct one thing. Right ascension is the east-west part. Declination is north-south.
So we have
I was trying to run to him.
No. Whatever. We confused ourselves.
Yeah.
What are the dimensions of the smallest object you've been able to detect?
Yeah, so the size of these things are hard to determine because so again, right ascension declination, that's more of a measurement of radius or of because you're looking at the sky, and if you can go back to one of the right there. So it says that its speed is moving at, like the top one says, I think 62 seconds. So seconds, minutes, degrees. It's 0.62, moving 0.62 seconds per minute. And so these things are like moving so slow. So it's hard to determine on our end how big these objects actually are. And also there's a lot of things in between us and that asteroid. So like there are some days where it's super, where you can see the atmosphere, like the waves in the atmosphere. So some of these images, these are the cleanest looking ones because we're showing them off. We don't want to show you the ones where it's like, oh yeah, put our best foot forward. Yeah. So yeah, we have a lot of moments where we're looking, and that's why I would say, or showed one of the harder images off, was because there is a lot of moments where we're staring at something and it is just atmospheric disturbance, and it's literally like hot air moving across. And so I'm holding up the ruler and being like, no, there's a little kink. And I'm like, okay, that's not an asteroid. So so determining just the size by the pixels, that's for the Minor Planetary Center. But our job is for them to be able to go, okay, like now we have more asteroids to study.
So you give them the target.
Yes. And then I think like they have like 2 weeks to spot it again in another image. And then then it goes on to the next pass preliminary detection. And like in a year or two, we get to possibly name it something that isn't a little more catchy than COR 0122. Oh,
What's the coolest thing you found in your research?
Coolest thing I found. I mean, I've only been working on this for a year, so I'm not that experienced in it. But the coolest thing that I found was when I was still very new to the team. It was, I think, my second image set ever, and I found five objects in one image set. And now normally we're lucky to get one object in an image set. So I got to find 5 on my second ever image set, and then that just set a really high bar for me that I've never been able to meet. So
yeah, it literally spoiled them because there's a term, I think if we go to the spreadsheet, we have found objects, yes, and then look at how many no's. Sometimes that means there's literally no moving, nothing. It's just a picture of the sky. And so we spend a lot of time convincing ourselves something exists. And so having 5, like we have Noah who found 6 in one, but generally it's like 1 or 2 if we do find anything.
Uh-huh.
You want to lap mic back?
No, it's okay. Have you guys found any UFOs flying yet?
not
You-
yet.
You know the answer to that. You know we can't answer it. I've seen you look over our shoulder. It's redacted.
We were told to say not yet. All right, were there any other questions? All right.
Oh yeah, I could have been doing this the whole time. Saved my research paper for last. This one was a paper it was a research project that I got to do thanks to the Oregon NASA Space Grant Consortium. They funded this project. I had to fill out some forms as well as get a letter saying that Dr. Coiner would be my mentor on this whole project, which definitely wouldn't have been able to do without him and some of his friends in the science community. This was my chance to actually do a hands-on research project and get an idea of what I'm in for in the future of science in this field. So So I should say my research was measuring the flux of pickup ions in our solar system. And the idea here is to measure pickup ions using available data from the magnetospheric multiscale mission, which is I'll talk about in a little bit, but it is an ongoing mission or NASA mission of satellites that are in space that measure many things, but one of the things we were looking at were pickup ions, which I will definitely explain here in a little bit. One of our goals was to try and identify the helium focusing cone and possibly a neon and oxygen focusing cone. Again, I will go into this, I promise. And then show that our methodology of data collection and calculations are viable. And with this information, we can help identify the composition of our local interstellar neighborhood to help build better models for our local space weather and a plethora of other just unanswered questions. So, big question, first things first, what is a pickup ion? So, space isn't just empty. We generally are told that it's empty space and that we're in a vacuum, but it is made up of many different smaller particles. Currently, our sun, not just the Earth is moving, but the sun is moving, and it has been moving through a supernova explosion, and so it's made up of a ton of different elements. And what we are interested in, what we can measure, are neutral interstellar particles, helium, oxygen, nitrogen, neon. There's a few others, but that was a lot of what our research focused on. Pickup ions are not solar winds. So the solar wind is the wind that is produced from hot plasmas that come from the sun itself, from the fusion reactions, and that we are all concerned about and measure and have. But pickup ions are incidentally charged particles from the solar winds. So this helium, oxygen, they are, as the sun moves, the pickup or the interstellar particles just hang out, and then the sun just comes in and blows them, and through that interaction, they pick up ions and then become charged, and that charge is a way that we can measure these. We can use tools to measure and identify the particles. So the magnetospheric multiscale mission, we actually had the ability to use information directly from this mission, which was so awesome to be able to look and be like, oh, this was from like 5 days ago. And so the magnetospheric multiscale mission, a current mission going on, is made up of 4 identical satellites. So each one of these satellites, and they're literally, they have the same tools. There's a lot of measuring equipment on it. They can measure magnetism, temperature, solar wind intensities, direction at their in or direction of the solar winds, as well as pickup ions, which is what we were looking for. There's a specific tool. We'll talk about that in just a second. The main study of this mission is to study Earth's magnetosphere. So where is the satellite currently? It orbits around in the magnetosphere here, and it generally stays in this area, or this is where we want to get most of our data. With the solar winds coming in this way, they push the over here, the magnetic fields. And this is kind of a bad spot because there will be a lot of coupling and decoupling, and it will mess with our data. So we're looking for time frames, and I will show you how we kind of figured that out. But a lot of the data that we have currently for pickup ions that I could find was from missions that were about 20 to 80 astronomical units away, which one astronomical unit is the distance between the Earth and the sun. So anything between here and here is less than 1 astronomical unit, and a lot of where we care about, where we live, is right about here. And so having data that isn't over here would be useful to us. So a lot of the missions like Ulysses or Voyager, that's where a lot of this data comes from. But with the MMS, we're able to collect data of 1 astronomical unit or less. And so we can see on a very local level the impact of our local space weather. So we use the Hot Plasma Compositional Analyzer, the HPCA, which is actually an equipment that was tested by Dr. Roman Gomez, which is a colleague and friend of Dr. Coiner's. He was a huge collaborator and one of the people that led us into part of his research. And this is actually a picture. I couldn't find one, and then he sent us this picture that he had on his phone. So it measures pickup ions. It was our main data collection tool. It has all the bells and whistles, 63 channels, but we ended up having only 16 because data is expensive. So decimating that down and transmitting it to us in 16 channels, a lot cheaper, a lot easier to get access to, a lot quicker for us to get data as well. And it measures in nanosecond intervals, 56 or 256. But generally, that piece of equipment, I believe, is this one right here. Might be this one or this one of those two. So kind of gives you a little bit of an idea of what we're looking at in size. This is how it works. So a pickup ion will go in here, and it will go through a energy analyzer, which this is a cross section of this right here. So this bend matches this bend. This is where the ions come in. They come in here, go around, get analyzed. So part of it is the bend, and then this measures time of flight. And so we use all of this data to, we will end up using all this data to figure out certain things, certain behaviors, and types of materials that are types of molecules that are going through here, or the helium, specifically helium ions. We also collected information for oxygen and nitrogen, or oxygen and neon. Thank you. So how we gathered our data, this comes directly from SWRI, the Southwestern Research Institute. And this is from one of the people's, or from their server, and we had to compile data. So one of the first things we had to do is find pristine solar winds, so times that were ideal for us to get our data. And so this is an example of a day of pristine solar winds, which happened to be December 7th. This is from MMS1 of hydrogen. We're looking for helium, but hydrogen was a really good indicator because there's just a ton of it, so we can make some assumptions. There were 4 of these images, so we just got to pick which one was our favorite one and kind of make assumptions off of it. So we have the first level here, which is just flux, and it's pretty easy to determine what's going on. I mean, not really, but it's easy to see that it's not full of too much noise, which we'll show in the next slide. We're looking for densities to remain pretty steady. Even these peaks aren't that bad. We'll talk about resolution here in a little bit. And then one of the more important things is consistent wind. So this is the X direction velocity in kilometers per second. This is Y and Z, but we're looking for this to be just basically rather consistent and below about 300. And then these last two are just temperatures, which we can use to infer magnetic coupling and decoupling of the magnetosphere. We want this to stay relatively clean as well. So now we get to learn, you guys get to learn how to read these things. So we have an example of a bad day. Comparatively, the flux there's a lot going on in the flux. And then we end up seeing that this is all over the place, as well as these numbers comparatively. This goes up to 11, this goes up to 37. And so it gets harder and harder to read. We would probably not use this just because of this resolution here. We can't tell if it's 300 or like 600. Well, we would be able to tell 600. So somewhere in 300 area, maybe. But if there was a huge spike, it would be hard to see. There's a disconnect in our day, as well as the temperature spiking. So, and then, a disconnect and then a reconnect where information was dumped in. It just like freaked out and threw a bunch of data that it had collected over that span of 2 hours. So this is the heart and soul of what our equation ended up being after a lot of talk and discourse between Dr. Coiner and Dr. Roman Gomez, but we finally got an equation that we would use. And this was the heart and soul of our data. Once we got the data, we would find a way to we had to find flux, which is the energy, basically the energy push that, and we would do it as counts, and the geometric factor, which is the size of the equipment, the collection equipment, energy, and then acquisition times. So know your audience. So I brought graphs, and here's what we ended up getting on our first go around. And what we were looking for was helium flux with a peak of what we assumed was around December 7th. So pristine solar winds, what we figured we would be in the focusing cone late November until early January? Yeah. Okay, yeah. So early January. So that was kind of our main focus for this one research, this one topic right now. The idea is maybe further on we can identify more times or identify different focusing cones, but right now we were focusing on helium because we had some assumptions and easier to read because we know that we're going into a helium focusing cone. We just need to be able to, or we want to see if we can measure the pickup ions for interstellar particles. So we ended up with this huge spike here from this day. We just wanted a starting point, and this just ended up skewing all of the results we ended up having. Each one of these lines is one data point for time, and each one of these data points probably took about 2 to 3 hours to compile each one with our math and our equations and just gathering data in general. But we were looking for a peak of this day, and the way that our collection worked was we didn't see this results until after we were able to actually put everything together. So to watch this actually get somewhat of an expected result was amazing, but this peak here was a little disheartening. So we modified our equation a little bit and made some more selective choices in how we how we analyze the data. And so we ended up taking out some of the channels so that we can get rid of the solar wind, which was for us like a background noise. So like it would be kind of like trying to hear somebody talk while next to the highway. Like we're trying to pick up that voice while cars are rushing by. And so one of the ways that one of our methods ended up actually showing that there might be some viability to this, because all of the rest of this graph from here on out went down proportional to each other, whereas the one off day ended up going down considerably, especially compared to the rest of our days. So we ended up modifying our analysis as we were going along. So there's still a lot of process and a lot of questions to ask. And but with that data, we ended up getting a very awesome fit graph here that this is the actual data that we ended up with, excluding that November day. And this is the fit graph, and here is about where we would expect the peak of the helium focusing cone, where just all of the helium would just basically focus. And it was just a very cool experience to go through and get a result. Now we have a ton of other questions that came from that can be answered, or we could ask later. With time constraints, there was only so many things that we could do. Once we got this, it was just like, okay, now put it together in a speech. We'll ask that next year or next time we get funded. So one of the cool things, though, about how we collected our data was that we also have not just helium, but oxygen and neon. Those were part of just incidental calculations. We have them here. One of the other questions is like this blue line is the helium focus, or the helium particles. But we know that there's more helium out in space than there is hydrogen or neon. So why are these numbers so much bigger, as well as this like spike, and why does it fit in with this focus, like the peak of our focusing cone? And does every year look this way? There's just a ton of questions that we can ask again, but we need more time. And it was very awesome to do this as a research project, because just learning, asking questions, and then everybody around me being like, that's actually a really good question, I don't know, or I will ask, or we just made assumptions working. One of the biggest thanks is to Joey. He was the person who had collected all the data, and at one point didn't necessarily, it wasn't our fault that the server crashed, but we are somewhere on the server crash reports, and he didn't blame us for it, even though 8 hours of research. Not just us, but everybody at SWOCC lost 8 hours of work. So he wasn't even mad. He was just like, what did you guys do so that we know how to fix it? So that was another cool part of just like, we made a mistake, and everybody's just like, okay, cool, that sucks, but. And then Dr. Roman Gomez, who was definitely in the middle of doing a lot during a research project, and still took time to answer all of our incessant questions on the HPCA and what he found in his research. And then, of course, Dr. Aaron Coiner for almost more or less pushing me along to keep doing this. And having this experience was awesome. It would have helped if you did have a cattle prod, but anyways, so they're my citations. So any questions? Okay, cool. Because you get me talking for like 45 minutes on this.
We'll have to work on the one thing. The next question that we have is, because we have those two spikes that are in the focusing cone. It's which one is the broader focusing cone, and how do we confirm them? But we'll do that this summer. All right. I want to thank everybody for coming. I want to thank all of the students in particular, and the students of Dr. Dana Pertermann, who had done the posters in the back. If you didn't get a chance to look at the posters, please do so as we wrap up. We do this type of symposium at the end of every year. We look forward to continuing to do those with our various projects. We also have our physics and astronomy lecture series, and I know Dr. Pertermann has a sociology and anthropology lecture series that she's been building as well. So we encourage all of you to attend as many of those as you can. And as far as the student researchers and everything, we do ask that if you didn't have a chance to, please sign in to our sign-in sheet by the door. That gives us an idea of how many people were here and gives us an idea of how much interest there is to continue. And one last ask, we do have our donation bucket that we use to basically help the student researchers with some supplies if they need to, or we also use it to help fund guest speakers that are coming in. So if you feel so inclined to donate, please feel free. We appreciate everything that the SWOCC community has done for us, and we look forward to more research in the next year. And with that, you guys can all go home.